Okay, hello everyone. It's our great pleasure today to have Marius Dadarlat from Purdue. Marius is going to talk about cohomological obstructions to group stability. Marius, please take the floor.
Thank you very much. Thank you for the invitation and greetings to the people in the room. I know you. So, all right. So we'll consider certain properties, stability with emphasis on non-stability of discrete groups. So I'll start with the definition. So we consider discrete countable groups, and we call gamma, and we call such a group uniform to uniform stable, abbreviated UU stable, if whenever we have a sequence of maps from the group to the unitary groups, n is variable, which are approximately multiplicative in a uniform way. So see, I take the supremum of the defective multiplicativity over the group, and I want that to converge to 0. So see, if you denote this by epsilon n, what's in the bracket here, okay, so such a map, okay, rho n is called an epsilon n representations. So this is Kazhdan's terminology, okay? So we have a sequence of epsilon n representations with epsilon n converges to 0, okay? So we impose a very strong condition, and we ask that whether or not such a representation can be approximated, such an sequence of uniform almost representation can be approximated by true representations, also uniformly. Okay, so this explains the terminology. We impose a uniform condition and we ask for uniform perturbation. All right, so now I will also consider a related condition, which is called uniform to local stability, UL stability. So the assumption is the same. We have a sequence of epsilon n representations with epsilon n converges to 0. But this time we are asking for a weaker perturbation, namely, we ask if there is a sequence of representation which pi n, which approximates rho n only pointwise. Okay, so the same strong condition, but we ask only for pointwise approximation. Okay, so a group with this property is called uniform to local stable. All right, so now one can visualize both definition on the same diagram. Okay, so I have a sequence of epsilon n representation, and I want to perturb them uniformly to genuine representations or pointwise. Okay, and since it's clear that uniform approximation imply pointwise approximation, right? Then of course, UU stability implies UL stability, whereas the other one, it's unclear but unlikely, and of course, it's not true. So, few words about the history of the subject. In 82, Kazhdan proved that all amenable groups are uniform to uniform stable. And in the same paper, he showed that the surface groups of genus at least 2 do not have this stability property. Okay, so now let's discuss each property. Okay, so now I start by reviewing the definition. Okay, so you see a sequence of uniform approximate representation, and I want to perturb them uniformly to proper representations. Okay, and there are several papers on this subject. Burger, Ozawa, and Tom, they call this property Ulam stability. And what they showed is that if one considers the comparison map between bounded group cohomology, H2, and the normal group cohomology, if this map is not injective, then gamma is not going to be UU stable. So maybe I'll say one word about the bounded cohomology. So its definition is similar to the definition of the group cohomology, but we impose that all cocycles are bounded as functions defined on Cartesian products of gamma. So it's like L infinity cocycles. So now, by previous work, by Epstein and Fujihara, it is known that the kernel of this comparison map is non-zero for non-elementary hyperbolic groups. In fact, it's a huge group. It has the power of continuum. So therefore, by Burger, Ozawa, Tom, the non-elementary hyperbolic groups are not uniform UU stable. Okay, so this is a vast generalization of Kashdan's example, surface groups. Okay, and now perhaps I would also mention here an example. So if you look at the free group is not being hyperbolic, it's not UU stable, but right. So what is the argument? Of course, this is the argument, but the classifying space of F2 is the figure 8. So H2 vanishes. Okay, so it's possible that the cohomology is 0, and this group is huge in this case, of course. And I say that evidently this is UL stable, and indeed. So if I'm so given the maps rho n, okay, so we can define the representation by just setting pi n of s. It's rho n s for S generators, you know, then extend to a representation. Okay, so for the free group, it's nothing to approximate the uniform approximate representation by genuine representations. Okay, so I'm emphasizing this just to keep in mind that the perturbation we are seeking is very strong, as opposed uniform, as opposed to local. All right, and let me say just 2 words about the proof of Burger, Ozawa, Tom. So we have the comparison map, and now here is a description up to isomorphism of the kernel of this comparison map. Okay, so it's isomorphic to the group of maps. These are called quasimorphisms in the literature, such that they are uniformly, you know, the effect of being homomorphisms is not small, but it's uniformly bounded. And then if we restrict such map to cyclic subgroups, they are homomorphisms. Okay, and of course this set contains all homomorphism from gamma to R. So, and then if it's larger, you know that then the kernel is not equal to 0. Okay, so what was the argument of the paper I mentioned? So if omega, it's a quasi-homomorphism, which is not a homomorphism, then all one has to do, I mean, this is what Burger, Ozawa, Tom did, consider this map to the unit circle, e to the 2 pi n omega s. Okay, so this is going to be a uniform approximate representation, so it's one-dimensional, but it is not uniformly perturbable to any homomorphism. So if you take any n and then any representation you might take, any homomorphism to gamma t, so you have this error. The distance is at least root 3. Okay, so this is very non-perturbable. All right, so in contrast, they show that higher rank group of this type, SL and Z, are not, they are stable, okay? And then there are subsequent work by Lubowski and collaborators on this subject. But this is not the focus of my talk, but I just wanted to review briefly some interesting results on uniform to uniform stability. All right, so the focus of the talk would be to uniform to local stability. Okay, so again, I review the definition. We impose a strong condition, uniform asymptotic multiplicativity, and then we are hoping to perturb locally pointwise. And now, as it happens, Kashdan proves, remember, I said that Kashdan proved that the surface groups are UU stable. But if one inspects his proof, actually, he gives a stronger result. In fact, he shows that these groups, the surface groups, are not even UL stable. His argument was different. In fact, his argument is the same as the winding number argument that was rediscovered later by Excel and Loring. Okay, so here it's a brief review of the surface groups. So they are fundamental groups of G-hole tori. So here I made this example where gamma 2, of course, is the fundamental group of this surface. All right, so there are these examples of groups which are not even UL stable. So, and then I wanted to understand, are there other examples, or what is what would be a natural context for in which to understand these groups? All right, and here is the result that I have. So if M, it's a close connected Riemannian manifold, which has sectional curvature. So this is a tensor at all points. I mean, it's a function less strictly negative. I mean, being compact, it's enough to ask that it's negative at each point. So, okay, now assume that the fundamental group of the manifold is residually finite, and then assume that one of the even Betti numbers do not vanish. So maybe I should say this is the dimension of the cohomology group. So one of the even cohomology groups do not vanish. Then the conclusion is that gamma is not uniform to local stable. Okay, so now maybe a few remarks are in order. I will make remarks on these assumptions. See that there are two key assumptions here. Now, M, it's sectional curvature, it's non-positive. So and then it's a general result that all fundamental groups of such manifolds are hyperbolic groups. And an open conjecture is that all hyperbolic groups are residually finite. So, of course, that's very difficult. So, but you see, it is conjecture. This part, it's automatically conjectured to be true. So, would not be an assumption. So, what about the cohomological condition? So, if the manifold is orientable and even dimensional, then of course it has a fundamental class. So the top Betty number, it's automatically non-zero. So see, if the manifold it's even dimensional and orientable, the second condition is automatic. So what about the even dimensional case? But I'm assuming orientable or dimensional. Then it suffices to ask that just some Betty number in dimension any dimension from 1 to 2n should be non-zero. And why is that? Because by Poincare duality, bi it's b to m to n plus 1i. Okay, so this is n. Okay, so let's say that I it's odd, then 2n plus 1 minus I, it's even, and would be right. So therefore, we have the assumption it's also satisfied. So we have more flexibility, just some Betty number. All right. And now I'll discuss some examples. So we consider the Lorentz group, SON1. This consists of matrices with determinant 1, matrices which preserves this so-called Lorentz matrix, right? So if the metric, this is the analog of being a unitary. Well, in this context, the matrix is not given by a scalar product, but it's the same concept. All right. So I consider this Lorentz group. Okay. Then the special orthogonal group is the maximal compact subgroup, and then the quotient is the classic hyperbolic space, n-dimensional hyperbolic space, and its scalar curvature, sectional curvature is constant. Actually, here it's at all points it's -1, and then gamma. Okay, so if I take here I said gamma, so then I consider gamma subgroup. Okay, and then gamma, would be, I will need a co-compact lattice. So it acts on HN, see, because it acts to the left on this homogeneous space. And then the corollary is that if gamma it's a torsion-free co-compact discrete subgroup of the Lorentz group, then it is not UL stable, right? Because now all the assumptions are satisfied. So this is the manifold, and then this is even dimensional, it's orientable, so here there are no conditions. Of course, there is this condition that co-compactness. So this recovers the Kazhdan results because the surface groups are contained in the Lorentz group SO2-1. Okay, what about the odd-dimensional case? Okay, in the odd-dimensional case, we need information about Betty numbers, and this question was considered in a recent paper by Bader, Lubowski, Sauer, and Weinberger, in which they wanted to determine. Okay, so I'll explain. So here it's I'm not stating the most general result in this context because it's technical. So again, we are in the odd-dimensional case. I consider a co-compact lattice, and one assumes that it's arithmetic, large dimension. Okay. So then the theorem says that there is a finite index subgroup gamma 2 of gamma 1, such that all finite index subgroups of gamma 2 have non-vanishing even Betty numbers. Right, so they prove this in order to establish what I call local to local instability of such groups, or matricial stability. So they applied one of my earlier results, which had assumptions on cohomology, and then they showed actually this using several classic results. All right, so therefore, as a corollary, now I'm taking care of, well, giving some result in the odd-dimensional case. If gamma it's a subgroup as in the theorem above, then it's also not UL stable. So, that's the situation, what is known in the odd-dimensional case. All right, so now maybe make it a little bit more concrete. So one can change this Lorentz metric, but that will not change the group. So so it's the same metric, but we throw it there an integer which is square free, for instance, a prime. Then one can consider the ring of integers of the extension of Q by root P. In this case, the ring of integers, it's Z plus Z adjoint P. Okay, and that somewhat older result is that GO is a co-compact arithmetic lattice in G, which contains many congruous subgroups. So you see, now the subgroups can be obtained as congruous subgroups, such that the first Betti number it's positive. But that's enough, because in the if n was even, we are done. If n is odd, we can apply the reasoning from before. And maybe I'll say this word, just one remark. So you see, for the Heisenberg group, you can have Heisenberg group with coefficient in R, but then Z, it's a lattice in R, and then you have the Heisenberg group with coefficients in Z. So you see the construction above, this is the flavor with the ring of integers, but it can be done generally. All right, so now I'll say a few words about the proof. So it relies on various results from on Novikov conjecture or Baum-Kohn due to Kasparov. And so remember, we are dealing with a manifold with strictly negative sectional curvature. And most people are more familiar with the assembly map, but the initial approach of Kasparov was based on the dual assembly map, and I will give a little bit of background. So in his Invenciones paper on Novikov conjecture, Kasparov proved that the dual assembly map, which goes from the K homology of the group algebra to the K theory of M. So maybe I'll write here that, for an algebra K0 of A, K homology is KK AC. Okay, so the dual assembly map is surjective, right? So I mean, in this area of Baum-Kohn, Novikov, right? The philosophy is that there is this duality between the group C star algebra or reduced group C star algebra and classifying space. There's some sort of generalized Poincaré duality, that the K theory of one object, it's isomorphic to the K homology of the other object, and the other way around. K homology of this isomorphic to the K theory of this. And this is the context here. All right. So now these K homology classes, right? Maybe we should mention the Kunz picture. So they consist of pairs of representations. So here I'm considering maps which are multiplicative but not unital, such that the difference is compact, right? This is the so-called a Kunz pair. And every element in the K homology of C star gamma is represented by such a Kunz pair. All right, so now our innovation here was to consider the subgroup of consisting of quasi-diagonal homology classes. Okay, and you'll see in a moment why this is helpful. So what do I mean by this? So I consider Kunz pairs such that one of the homomorphisms is quasi-diagonal, meaning that its image is a quasi-diagonal subalgebra of V of H, which it means that there is an approximate unit of the compacts on V of H, which commutes asymptotically with the image of phi prime. But if that happens, since the difference is compact, will commute asymptotically with the other one. Okay, so really these are Kunz pair consisting of quasi-diagonal representations. All right, so what about examples? So the first time I apply this, I consider groups where the group C star algebra is quasi-diagonal. But then Kubota had a very clever idea of using intermediate algebras, and then using that one shows that if the group is residually finite, then the restriction of the dual assembly map to quasi-diagonal K-homology classes is still surjective. Okay, so not only that the dual map is surjective, but even if I restrict it to quasi-diagonal elements, is still surjective. And this can be generalized then to quasi-diagonal groups, but I will not address that. Okay. Now, there is, I would say a few words about the dual assembly map. In general, this is defined using the Kasparov product. But in this case, when one restricts this to quasi-diagonal classes, it admits a much simpler description, which is very well suited for our goals. Okay, so we start with two homomorphisms. So I'll just write, remember, phi s minus phi s prime, it's compact. Okay, and these homomorphisms, so I can assume that phi prime s, actually it can be taken in if the group is residually finite dimensional. I can take phi prime to be direct sum of finite dimensional representations. Okay, and then we can compress this to finite dimensional corners, Pn. So see, rho n, rho n prime would be the compression of Pn, P prime, Pn. Okay, and this is a representation, but then rho n, Pn, the restriction of E, Pn, this is no longer a representation because Pn does not commute with phi. However, since the difference is compact, Pn will commute asymptotically with the image of phi, and therefore rho n would be asymptotically multiplicative, but just pointwise. Okay, so the useful observation here is that how do I get, this is a technique that I used here to obtain interesting asymptotic homomorphism. So how do you obtain that? We consider K homology classes, we assume quasi-diagonality, and then I compress the Kunz pair, and then I get these approximately multiplicative homomorphisms. And they capture quite a lot of topological information from the data, right? So here I'm repeating what I said here in the first part, but now I'll describe here the dual assembly map. So we consider the so-called Pischenko projections in matrices over C of M tensor C of gamma, and maybe I'll give you an idea of how that projection looks like. Okay, so L gamma sum. These are some partition of unities. This is a partition of unity on M. Then Sij are group elements. And then Eij are matrix units. Okay, so L gamma is a projection in matrices over C of M tensor. Okay, I need some more space here. Okay, so L gamma is a projection in matrices over C of M tensor. It's in the group algebra, but I can put C star gamma, doesn't matter. Okay, so that's the Pischenko projection. And now imagine I have a representation of gamma, or even a map. Yeah, actually it's a map. This is actually a completely positive maps from C star gamma to some other matrices. These are the compression. Okay, and then if I do identity of M tensor C star gamma, I can apply it to elements in C of M tensor C gamma. So I apply it to L gamma, and what I get, this is an element in matrices, in some matrices over C of M. Okay, so you see from an approximate representation, I push forward the Pischenko projection, and I get elements in matrices over C of M. And then if rho is very multiplicative, this element would be almost a projection. So I can perturb it to a projection. Okay, so this is the construction. So I take the Pischenko projection in matrices. Then I push the Pischenko projection forward in matrices over the manifold. Then by functional calculus, I perturb them to genuine projections. So you see, so in this way, I define an element in K0 of M. Okay, so this is a description of the assembly map, of the dual assembly map using quasi-diagonality. Okay, so I sent to this element. And then we know that this map is subjective, but what we discussed. All right, so maybe I'll finish. Okay, yeah, all right. Yes, so this map is subjective. Now, all right, so the map is subjective. So what have we gotten so far? Okay, so let's keep in mind that in this way we constructed the maps rho n and rho n prime, but rho n prime, these were already homomorphism in or representations. if the group was residually finite. So rho n carries the interesting information. Okay, we would like to use rho n. So what do I need for about rho n? Should be a uniform approximate representation, which is non-perturbable. Okay, unfortunately, it's only locally approximate multiplicative. But in order to discuss the obstruction as a warm-up, we'll just let me run the argument for the result that gamma is not local to local stable. I have not defined that formally, but now should be clear what it means. I assume that the morphism, the rho n, is only pointwise asymptotic multiplicative, and I want to perturb it pointwise to representations. Okay, so now, based on our description of the dual assembly map, okay, so I push any class to a difference of bundles. Okay, so now assume that rho n prime perturb to genuine representations. I mean, rho n is already a genuine representation. So assume that rho n can be perturbed to a genuine representation. Okay, in this case, you see, I don't have to do any, when I push forward the Mishenko bundle, I don't have to do any functional calculus. Because if I perturb a map to a nearby map, and I apply it to a projection, the images will be close to each other. So in this case, I just apply homomorphisms. And what I said here, I get bundles, which I called, these are flat bundles. Okay, so what is a flat bundle? A flat bundle on a space, it's a bundle constructed from by gluing trivial bundles using constant cocycles. Using constant cocycle. And I remind you that you have the formula for L gamma. So if I apply a homomorphism to the Mishenko line bundle, so what I have, what maybe was identity. So I have the partition of unity, tensor phi n Sij, tensor Eij. So see, these are unitaries, okay, these are unitaries, and they are constant, you see, they are constant unitaries on overlap of maps. So see, this is a projection or a vector bundle constructed using constant cocycles. Okay, so how is that useful? So now I put things together. So since this map is surjective, assuming perturbation L stability, I obtain that K0 of M is generated by flat bundles. You see, the image was flat if I can do the perturbation. Now, the Chern classes of flat bundles vanish over Q. This is by a remark of Milnor. So the proof is easy. It's Chern-Weil theory. So if the cocycle it's 0, then when you take covariant derivatives, the curvature vanishes. So the Chern classes vanish. On the other hand, the Chern character is a rational isomorphism, right? So if all I have in K0 of M is flat, the Chern character vanishes except in dimension 0. So therefore, this implies that the cohomology of the manifold should be 0. Okay, but I haven't emphasized this. The manifold here is the same as B gamma. I mean, due to negative curvature. So this is B to I. Okay, so that's the argument. And in fact, what I did here was to outline an earlier result that I had, which applies to much more general groups, but concerns only local to local stability. So if a discrete group is MF, okay, so MF means that gamma embeds in the unitary group over product of matrices over direct sum of matrices. And if it's coarsely embeddable in a Hilbert space, if sum of the Betty number, even Betty number, does not vanish, then the group is not local to local stable. All right, so now with this in mind, I will go back to uniform to local stability. Okay, so now here we have a difficulty, a serious difficulty. Why? The map constructed by quasi-diagonality arguments, as I discussed before, only gives maps which are approximately multiplicative pointwise rather than uniformly. Okay, so that's a huge headache. That's a huge headache. All right, so then one has to refine the methods. And in order to explain briefly this, I will go back. I will explain a general principle. Okay, so how does one construct interesting and non-trivial approximately multiplicative maps? Okay, so I just illustrated how to do it using quasi-diagonality. Okay, so if I start with an interesting K-homology class for the group algebra, and then if I have quasi-diagonality around, I compress and I still collect a lot of information. All right, now Gromov actually quite early in the 80s, and then Kohn, Gromov, and Moskovich, they had a different approach. They will construct asymptotic homomorphism, approximate representation using almost flat bundles. And almost flat bundles were constructed using geometric arguments. And in many situations, this approach based on quasi-diagonality, it's much more efficient. In fact, constructs many more approximate, even approximate almost flat bundles than the geometric method. But to put this into a context, you know, what is the general picture here is that, so I will consider the classifying space of a discrete group, and its cohomology is the same as the cohomology of the group. And for simplicity, we'll assume that B gamma is a finite simplicial complex. Okay, so now if one has a genuine representation of the group gamma, Atiak and then Atiak-Segal, they constructed a flat vector bundle on B gamma. Okay, so the construction was something like this. So you see, E gamma, you have this representation. So if pi goes from gamma, it acts on Cn. Okay, on let's say Un. And then you take this diagonal action of the group and this project. So this is a flat bundle. And then a classic theorem from differential geometry is that if you have a flat vector bundle, in fact, you can take monodromy. This is the smooth case. You can take monodromy in that flat vector bundle, and then you get back to genuine representation of gamma. Okay, so in one direction, this method was used by Kohn, Gromov, and Moskovich. So what we did, starting with almost flat vector bundles, which were constructed by Gromov by geometric arguments, one considers approximate monodromy. Okay, so actually parallel transport refers exactly to this. Okay, so to this arrow, parallel transport. And then one constructs almost representation. So this was the method of Kohn, Gromov, and Moscovich in their announcement on Novikov conjecture that they used. Okay, now it turns out that just like in the flat case, one has a correspondence between almost representations and almost flat vector bundles. Okay, so and in fact, the method of going the other way is just exactly what I described. Okay, so this method, the method that I used when I explored the other implication, is the push forward of the Mishchenko line bundle. Okay, so see, one can start with almost representation and can push forward the Mishchenko line bundle and one get an almost flat vector bundle. Okay, and this is a technique that to go back and forth. Now, for L stability, that was not needed. Only one direction was needed, but in order to obtain uniform approximate representation, okay, one has to use both techniques. Okay, so okay, right. So in order, I'll finish in 1 minute. Okay, so what one does, okay, so maybe I'll just illustrate here. So the way it's constructed is that one starts with an interesting Cohomology class. Okay, then by quasi-diagonality, one constructs these maps rho n prime. Then by pushing forward the Mishchenko line bundles, one gets projections En prime and En. So this is the, okay, so from projections, you can go to bundles. Okay, so these are bundles, which are almost flat. Now you need them to be almost flat, also in the smooth case. Okay, and now by parallel transport, one gets new representations, which maybe I'll call phi n and phi n prime. Okay, and this is uniform. This is epsilon representation. And using this correspondence, the approximate monodromy correspondence, this is the homomorphism which is not perturbable. So one has to go back. So first, one starts with a non-trivial Betti number. Then one hits that with a K homology class. Then by quasi-diagonality, one obtains interesting maps, push forward, get a bundle. Okay, but these approximate maps are only locally multiplicative, but by exploiting the negative sectional curvature, then one proves that these representations are uniform. And that the technical results essentially are in the literature. So, you know, there are estimates by Buzer, Harsher, and Gromov, which has to do with the area. The key property is that if one takes a geodesic triangle in such a manifold, its area is always bounded by K, that's the curvature, in absolute value times pi. And then when one does parallel transport, this is controlled by the area times the curvature, but almost flatness means this is small. Okay, so there's just an outline. So yeah, I'll finish here. So.